it's a very engaging, the workshop here. A lot of questions and good presentation. Awesome. Okay, let's move on. So we have got the Luke joined our workshop, and he's available right now to present to us about the Libre SOC and Cray-style vectors for open power. And Luke, Kenneth, Cason, Layton. He has got 4 names: first name, 2 middle names, and last name. Anyway, he can explain to us later. Specializes in Libre ethical technology. He has been using programming and reverse engineering computing devices continuously for several years. As a B engineering honor in ACGI in theory of computing from Imperial College, and recently put that education to good use in the form of LibreSOC project, an entirely Libre licensed 3D hybrid CPU, VPU, GPU based open power. Open power, that's a very important one. He writes poetry, and he has been developing a HEP physics theory for the past 36 years in his spare time. Luke, I welcome to the the workshop as well as the presentation. Please go ahead and start your presentation. And I know that there is going to be a video played for you, and our research scholar Viba, will be presenting that video, and you can go ahead and answer the questions too. Thank you.
Thank you so much. So it's if we could play the video, the person who's very kindly offered to do that. I must apologize to everybody. I'm on a mobile broadband low capacity network, so I have to have somebody else play the video. If we'd like to do that, if we could start that. Is it? In the meantime, whilst the person is preparing that, Federico Ficarelli, there was a question that you asked, given the large instruction, does it make sense to throw hardware loops into the mix to save some front-end load? Well, that is exactly what we're doing with the Cray-style vectors SVP64, which is the draft extension we're developing as an R&D project. And so the first one that we are adding, we're calling it Remap. And I go into some bit of it during the video. We do the Remap system takes a standard array, linear indices of the elements 0, 1, 2, 3, 4, 5, etc., and allows a complete remap of those onto 2D matrices and 3D matrices. And we've just started adding in the logic for doing in-place fast Fourier projects.
Cray-style vectors for open. So I'm going to do this in a slightly different style talk. We're going to use web pages online, so you can actually follow along and see these links for yourself if you wish. They're at libre.org/conferences/2021. So a brief overview of the Cray-style vectors that we're adding. I was picked because it's already a set. There's an article online on Sigarch, it's simply called the typical you first have the operation there, but in the case of AVX 512, it's now up to 512 bits. You've got instructions for, you start off with the operations add, multiply, whatever, and you then multiply those by bit widths to do 8, 16, 32, 64, and 256, and now with Intel 512. So now, initially you had 40 instructions, now you've got 40 times 2, 4, 8. You get the idea. Then you have conversion instructions. Then you have some which are signed and unsigned versions of the thing. So you multiply by B16, so 264, 128 million multiplied by Pascal's triangle. Good there. Signed and unsigned, you double them again. But for DSPs, you double them. Well, actually, you multiply them by about 16 because you have high-low selection. So high, 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 low, 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 high, high, high. Then so multiply by 4. You start to see that it gets quickly out of hand. You know, what should be 70 instructions turns easily into 1,000 or 2,000 instructions. Craystyle vectors, on the other hand, they're ridiculously short. Now, the fundamental basis of Craystyle vectors is that you have like the old x86 ret instruction, prefix, which says, here's your base, I'd like you to repeat it n times. And in the Craystyle vectors, you have, in the original Cray instructions, you have an expression called setBL, which sets your vector length. Now, the actual hardware, it's hardware agnostic. So in your program, you write programs that literally the program doesn't actually need to know how long the vector really is. The hardware, it tells you, it's limited to this much. But that's at runtime. That's critically important, and it's a completely different paradigm from how SIMD operates. Now, we do things slightly differently, but it's effectively the same. And you have this for loop. So you have a scalar add, not a vector add, a scalar add that is repeated as far as the programmer is concerned. The VL times and VL vector length is dynamically selected at programmable at runtime. It's not hard coded into the program source code like it is in SIMD. So once you've got that basic concept, we've then added the ability that through tagging, as it's called, to set a tag as to whether the destination is a scalar or a vector, and whether the source 1 is a scalar or vector, and whether source 2 is a scalar or vector. And consequently, there's 8 possible permutations here, one of which is the original scalar add. So when all 3 of your the registers are marked as scalar, you have the original OpenPower v3.0b scalar add. It's quite simple. So the next bit on top of this is that you can add predication. Now, bear in mind, none of this is done by actually modifying the scalar v3.0b instructions. It's done via this context. So you've got the rep style prefix, which contains an indication of a desire that the scalar operations should be predicated. And basically, that you specify a predicate value which at runtime can mask out individual operations. And that's critically important for 3D workloads, video processing, vector processing, everything. It's the fundamental basis of AMD, Intel, and NVIDIA GPUs. Now, so that, if you can read a little bit about that, just search yourselves on that overview article there, Libre.org/overview. Now, I want to go a bit more over this article, which is the significance is deeply understated. Right. The more I investigate, the more I'm horrified at the effect that SIMD has had. That's not a joke. Here's your program. I think it's the standard DAXPR double add with x times y. Y equals ax. Y equals constant, scalar constant a times x, and you add that on. So it's just standard y equals mx plus c algorithm. Right. Now, the number of instructions, although this is for RISC-V vectors, it's exactly the same concept for any Cray-style architecture. You have your setBL here, where you attempt to do 10,000 or 50,000 or 1,000,000, but the hardware says, oh, actually, I've got only 4 lanes, or I've got 32 lanes, or I've got 1,000 vector lanes. It doesn't matter how many it has. It limits that the number that it's going to do to VL and puts it into a temporary variable here. Now this is important for later, right? Now, when your vector length has been set, load vector X will load VL entries into memory. Now it doesn't say that it's the way that it's done. That could be done one at a time, or it could be done if your hardware implementation is capable that you could do an entire 512-bit wide load. But it's up to the implementation to define that thing. So there's your vector load of Y. You're incrementing the pointers here. Here's the actual add. Now again, it doesn't say how. In the hardware, it hasn't. In the instruction, sorry, it hasn't said I am explicitly doing 4. I am explicitly doing 8, like you have to do in Cindy. But it multiplying by the constant a is subtracting the vector length from the number that have been calculated in this iteration through this loop from your count, your n count a0, and repeat if that count a0 was non-zero. But that's it. That's all it takes. Note the complete lack of SIMD setup and teardown. Okay, right. Here's what it looks like for MIPS, right? And which has a 2-wide SIMD, and you had to first. There's your main loop, which if you're very lucky, you didn't overrun the thing because you actually are called for n equals 0 or 1. Oh, here's your fringe code. Yes, you have to detect if it's a fringe here. And then if it's even if it's even you're done, and if it's awful, right? I've got some illustrations later of quite how bad this gets when you go up to 512 bit, 128 bit, 512 bit thing. But you should have that sinking feeling at this point. Now, here's a really useful illustration of SIMD versus vectors. Now, on the face of it, it looks like the SIMD instruction is more efficient and completes quicker because you've got 4 loads being done at the same time, you've got 4 adds being done at the same time, 4 multiplies and 4 stores. The problem comes, whereas the load, you're only doing 1 load at a time here, right? Therefore, it completes in way. Comes when you look at this and you realize that that is if it's a 64-bit load, that's 4 64-bit loads. That's 256 byte wide hitting the memory subsystem at once. And until you have, here's the kicker, because it's Cindy, until you have done all 4 loads, you cannot do the adds. Likewise, the caveat to Cindy is until you have done all the adds, you cannot do the multiplies. And correspondingly, only when all multiplies are completed can you do the stores. It's only 1 load, 1 store, 1 load, 1 load, 1 load at a time, and 1 store. But look, they're overlapped. Right? This is called chaining. Right? And if you were to compare like for like here, you'd have to do 1 load here, followed by another load in the 2nd cycle, and another load in the 3rd cycle, and another load in the 4th cycle, and only then, once you have performed all your 4 64-bit loads, could you do 1 row of adds. Then you get your 1 row of multiplies, and then you have to have store, a 64-bit store, and then another one here, and another one down here, another thing. So it's actually, if you work it out, and you're doing a like-for-like comparison of an array processor with 64-bit wide load, 64-bit wide store, you end up with much worse performance, much worse latency on the Cindy processor than you do versus the vector one. And this is something that's been completely missed. But not only that, it should be quite obvious that when you go to 256-byte wide SIMD, 512-bit wide SIMD, 1024-bit wide SIMD, the problems get worse, not better. You have to wait for the entire 512-bit data to be available before you can move on to the next thing. Whereas with the vector chaining, it's you get these inflows are much more efficient use of resources in your hardware, and a small completion time is better, and latency is lower. Now, this is so bad it's not even funny. Here's the integer version of that DAXPY version. That code. All right, it's using integer y and integer x, integer j. I compiled this for AVX 512. Let me shrink this down. Here's the assembly code. It's 273 lines of assembly. I thought this was a good idea. I'm confused and actually, in some ways, quite angry and embarrassed that this is how things work. If you look here, you can see what it's doing. The reason why it has to do this is because the alignment on SIMD is often to the boundary, so you don't just have a like in that the Cigar article, you had a fringe thing. You have a preamble stage where you have to get up to the alignment width of the SIMD operations. I believe is what's going on here. So it's going. Have we got one item in our array that's not aligned? No, jump over, doing jump. You get, because it's AVX 512, you get 15. I'm sort of shocked. Then you get the actual instructions of the inner loop to do and then afterwards you have to go through the same process of same cleanup process. I mean, it's awful, but I have to say, rather embarrassingly, it's the same thing for VSX on Open Power. Here's a string copy implementation for IBM Power 9. It's 240 instructions. The same thing has to be done. By contrast, here's the version that's for RISC-V. This is just a string copy, but literally that's it. It loads a vector of bytes. But here's one thing. No, sorry, this is a set vector length for getting vectors of bytes. Here's the important thing. There's something called fail on first, which is what happens here is that the vector length is truncated to an appropriate length that the length that the hardware deems appropriate. That's particularly crucial. This was something that was introduced with ARM SVE2. It makes sure that you don't overrun a page boundary. So the actual number of elements that are loaded is within the amount that the vector engine, the parallel vector engine, can deal with. You don't have to have that logic detection for the thing, but you can't have it anyway. You don't have to have that in the inner loop. If you attempt this kind of thing in SIMD, well, you can't actually do it because you have to attempt the load and then detect the page faults. That's in user space, but you can't do that. That's completely unsafe. We're adding this feature. It's called what's it called? Fail on first, but it has another one, speculative loads, as well. Now, next one here. I also, I'm sorry, I should have done this I've done this slightly out of order. I also did the IAXPY version in PowerPC with VSX. And again, you can see that the amount of code is extremely large compared to, I think it's about 5 times larger than the RISC-V string copy version. So unfortunately, to say, despite the fact that the achievement with IBM with the Power 9 and the Power 10 is absolutely fantastic. I think it just they missed the trick with vectors. Now, what we're doing is we're in the LibreSoft team is we're doing some demonstration codecs, video codecs. And one that came out particularly interesting was the MP3 algorithm, which has this is directly from FFmpeg source code. It's called the apply window function. MP8 DSP apply window floating point version. This is a macro which does 8 multiply and accumulate, and then 8 multiply and subtract. So here's the macro this does. And when you expand this out, we can parse in C for PowerPC scalar, you end up with over 400 instructions, 400 assembly instructions, because that macros end up expanding out to these massive numbers of subtract, multiply, and subtract instructions. So it's rather unfortunate. The same code for the SPP64, we're calling it, only ends up at 80 instructions, were actually 100 32-bit instructions. It turns out that we vectorized multiply and accumulate, and it turned out to produce the results that were too accurate. So for unit test purposes, we're doing them explicitly as multiply and add, multiply and add. So there's one here which is the add, and then there's the other one is subtract. Now, one of the important things about vector instruction sets is that they have what's called a Mapreduce mode. So you don't find this in SIMD because everything is in lane. So how can you add things that are interlane? You can't add interlane, whereas with vector instruction sets you can. And we did a bit of a cheat in this one, is that the Mapreduce mode, we're relying on the out of order execution of a standard scalar add. So RT is the scalar thing here, and RA is the scalar source, but it's a vector source too. And what this will do is, again, according to that simple for loop here, simple for loop, RA equal, it's a scalar source. So what it's doing is it's adding the register B onto A continuously. Right? There's nothing special here. It's nothing explicit. It's just putting the vector engine into a special mode, which performs a sum. So yeah, really quite straightforward. And it results in a reduction in the code size of a factor of 4. When you compare it against the Intel version, which uses SSE, I think it does, it's a factor of about 6. And you just don't have, in computer science, you just don't get those kinds of savings. It's perfectly normal for in some instructions to maybe have, factor 10%, 5% you add some new instructions. If you get a 2 times saving in power, that's enormous for adding a particularly new concept like the multiply and accumulate system, the matrix multiply assist. As I did, they're getting to, in power 10, they're getting 2.5 times power reduction in things, but you don't get a 4 times or a 10 times reduction in program size with associated reduction in the level 1 cache usage. So that was the first part of that. But the second part, we decided to go on to looking at the FFT, because that's part of discrete cosine transform thing. So this algorithm, the Curie-Tukey algorithm, is particularly known because it's an in-place algorithm where you perform these butterfly swaps, and you recursively perform the thing on the left half and the right half, and then perform then you go down recursively into those two, and then you at the level that you're currently at, you do this butterfly multiply and accumulates twin multiply, you add on one of them and subtract on the other, but you do an in place overwrite of the array in your pseudocode here. So you're creating P and Q from the S values, but you overwrite after the thing, right? So there's 2 stages to this. One of them is that if you do it in completely as an in-place algorithm, you have to actually do this bit reverse copy of your data. So what we decided instead was to add a bit reverse load mode. Sounds confusing, but what that means is that it's a special mode, load word 0 in bit reverse mode. So if the vector length is 4, then instead of 0, 1, 2, 3, which is binary 0, 0, 0, 1, 1, 0, 1, 1, we actually load from the bit reversed version of those, which is 0, 0, 1, 0, 0, 1, 1, 1. Right, and this is one of the key problems of I think you should see some of the algorithms for doing a bit reversal in a scalar instruction set. It's pretty bad. So why not put it in hardware? No, it's quite simple for us to do, and then we can have just one instruction instead of dozens. So here's a simple unit test which showed that that we've added this and it actually worked. The second step was the multiply and accumulate. What we wanted to do was to do this as multiplies and subtracts. So what we've had to do is add a special instruction. We call it FAT multiply and adds, but it's actually a multiply, add, and subtract. So the offset into the vector is automatically added, and I put this in, just to calculate that. Here's your multiply, and so it looks like the sort of code that you can see in the Wikipedia page and the algorithms that you can find online. But this should get us, a similar sort of 4-to-1 reduction in the code size for doing this thing. But the next phase will be to add a remap system. We've got an equivalent to the matrix multiplier system where you can actually remap the array into 2D or even 3D things. But what we want to do is to do these loops here and this one here actually as a single instruction. So we'll do a setup, some setup, and then you would literally you do one load with a bit reverse load, and follow it up with this remapping of the what would normally be array style loads. So we have a single instruction. I'm really not kidding. One single instruction, and it does the entire vectorized FFT in place. It's deeply significant because we should be able to get away with about only about 25 instructions. You should see some of the hand optimized assembly for this online. It's awful because it has to use explicit simply, and you have to use loop unrolling. The 600 hand coded assembly instructions is not unusual. Now, the only thing that we've got about this is we've got to watch out for is that the other aspects of this is that you get you end up hitting the same cache lines, and so our ongoing research into this will be make sure that the cache is designed so that it has multi-way cache tags, four-way set associative, to make sure that when the multiple FFTs are done, which are on the similar power of 2 boundary, they don't end up pushing data out of the level 1 cache. So that's where we are. It's just exploring them, taking the Cray style concept towards a modern take on it. One thing that unfortunately is very unfortunate is that the Cray style supergroup vectors were done in an era where performance of computers was, compared to today, is that it looks rubbish. But completely forgetting that if you pull the concept forward into today's modern processing nodes and geometries, you end up with something that's absolutely staggering. I'm really not kidding. Literally orders of magnitude reduction in program size and effectiveness, which translates to an effectiveness of the instructions. So thank you very much.
Thank you, Luke. I think it looks like some issues with the audio, but Luke, you want to say a few words?
Yeah. this is in draft at the moment, and we're funded by NRNet. So if there's anybody who would like to help work with this, they're more than welcome to do so and participate. We've got the simulator is up and running, and that's what we're using at the moment. And then we'll put it into FPGA as well. And when we're happy with it, we'll submit it to the newly formed ISA working group in Open Power. So I just wanted to emphasize that there's no restrictions on performance here. The gains that you get with the efficiency mean that when it's ramped up to something that's doing multi-way issue execution, you end up with far less power being used for to execute the same workload as on any of the current processors that don't have Cray style vectors today. That was what.
Any questions, Luke? Thanks for the presentation. And any questions for Luke, Arjun, panelists?
One thing
No,
I just
I'm
wanted
good.
one thing I did want to say was just to emphasize what Federico's question. Yeah, we are. These are hardware loops. We're literally doing these hardware loops with a remapping system and just investigating how to use that. But the thing is that we need the context, the equivalent of this rep instruction from Intel x86 to be able to do it, and using the scalar instructions as the primitive, the base. It should save enormous amounts of program size, which turns into level 1 cache reduction, and so on. So yeah. All right.
Sure. Thank you. Thank you for the presentation, as well as the time spent on this. And hopefully, we'd like to hear from you. The complete the LibreSoC, the GPU, CPU with the operating system running and all the stuff. Wish you all the best, Luke, for the wonderful
very much appreciated. Thank you.
Yep, thank you. And audience, if you want to try out anything on a kind of a core, LibreSoC core, which uses microwatt, the open power core, please do take a look at it. The LibreSoC, the website, and there are a lot of things people can do with that. And already a bunch of people looking at it and trying to run it, simulate it, and all. And
just a question from Richard Wilbur. Richard, yes, it is, Richard. It's available online on the if you go to the libresoc.org/conferences and then select Cineca 2021, I will have the video will be available. Link will be available from there, and it should be a better quality, and you'll be able to see it. Things.
Yeah, and also all these presentations will be recorded, and we will be sharing the thing in YouTube, in our Open Power AI YouTube channel shortly. It will take maybe 24 to 48 hours for us to just deliver that. So okay, once again, I'd like to thank Luke for the time he spent on it, and also presentation as part of this the Open Power and Cineca workshop.